So this is the second exercise of chapter 1 of linear algebra done right. The exercise can be found on page number 17 of the book. So the first question is, prove that minus of minus v is v for all v in capital V. So we can use the property of additive inverse to prove this. So if I take an element v and add minus v to it, I'll be getting 0. Similarly, if I consider the element minus v and add its additive inverse, which is minus of this element, which is minus v, is equals to 0. So this implies that both v and minus of minus v are additive inverses of minus v. So by the uniqueness of inverses, we can say that v equals to minus of minus v. Moving on to the second question. Suppose A belongs to F. F is a field. A here is a constant. And V is a vector in capital V. And AV is 0. Prove that A is 0 or V is 0. So to solve this, I can make two cases. Once where I consider A is 0 and once where I consider A is not 0. When I consider A is 0, then I have the condition that AV is 0, that is 0 into V is 0, so V is 0. So both of these conditions are satisfied. Next, A is not 0. If A is not 0, then A will have an inverse. So let's call the inverse of A as A inverse. And we know the property that A times A inverse is 1. And now V can be written as 1 times V equals 1 is nothing but A into A inverse times V equals A inverse times AV equals to AV is nothing but 0. A inverse into 0 is 0. So we have proved that even if A is not 0, V is 0. So the OR condition is satisfied. Here I have used the associative property. Moving on to the next question. Suppose V and W belongs to V. Explain why there exists a unique x in V such that V plus 3x equals to W. They are saying that V and W is already in V. So what I can do here is first find out what is x. 3x will be W minus V. X will be 1 by 3 times W minus V. So V plus 3x is nothing but V plus 3 times 1 by 3. I'm just substituting here. W minus V equals to V plus W minus V is W. So this shows the existence of X. Now I have to show uniqueness of X. To show the uniqueness of X, suppose what we can do is, we can show that there is another vector x dash that satisfies this equation here. Let's call this equation 1. So let x dash be another vector that satisfies equation 1. So it will be v plus 3x dash equals to w. Then 3x dash is equals to w minus v. And similarly, we have 3x equals to w minus v. Hence, if I subtract 3 times x minus x dash equals to 3x minus 3x dash equals to w minus v is 0. So x minus x dash is 0 and x equals to x dash. This shows the uniqueness. To show the existence, we just found out the x and substituted it. And to show the uniqueness, we assumed that another vector that follows these conditions exists, and show that those are equal. Coming to the next problem. The empty set is not a vector space. The empty set fails to satisfy only one of the requirements listed in 1.19. Which one? So, definition of a vector space, that is 1.19 definition. This says a vector space is a set V along with addition on V and a scalar multiplication on V, such that the following properties hold: commutativity, associativity, additive identity, additive inverse, multiplicative identity, and distributive properties. So here, additive identity, if this exists, then 0 will belongs to the set, which means the set can't be empty. So additive identity is not satisfied in an empty set. And if you don't have additive identity, you can't really talk about additive inverse. Moving on to the next question. Question number 5 says, show that in the definition of a vector space, the additive inverse condition can be replaced with the condition that 0v equals to 0 for all v in capital V. Here, the 0 on the left side is the number 0, and the 0 on the right side is the additive identity of capital V. Just to make sure that we can distinguish both the zeros, we can write it as 0f, the 0 coming from the field f, times v, equals to 0v. This 0v will represent the additive identity of capital V. This I can call it as statement H. So what they are asking us to do here is, this is the definition of vector space, and we are asked to see what happens if we replace the axiom of additive inverse with the statement H. We also know that from statement 1.29 that 0 times V is 0 for all V in capital V. So H is nothing but a consequence of the axioms of vector space. So now what we will do is, we will drop this axiom of additive inverse and we will replace it with the statement H. Now let small v be any element in capital V. In the field F, we have 1 plus minus 1 is 0. So in the statement H, I will replace 0f with equation 1. I will get 1 plus minus 1 times V equals to 0v. And to equation 2, I will apply the distributive property. And when I do so, I will have 1 plus minus 1 times V equals to 0v. So what does this mean? It means that minus 1 times V is an additive inverse of V. Thus, the existence of an additive inverse will follow from the assumption H and the rest of the vector space axioms. Moving on to the next question. Question number 6 says, let infinity and minus infinity denote two distinct objects, neither of which is in R. Define addition and scalar multiplication on R union infinity union minus infinity as you could guess from the notation. Here what we can do is, we can think of infinity and minus infinity as vectors, and all the entries in R will be scalars. So specifically, moving on, the sum and product of two real numbers is as usual, and for T and R defined. So we have two vectors and we have R, and we know, and they have said that the sum and product of two real numbers is, the usual thing that you already know. And they have given what T infinity and T minus infinity mean. So T is a scalar and infinity is a vector. So T infinity equals minus infinity when the scalar T is less than 0. T infinity equals 0 when the scalar T is 0. And T infinity is infinity when the scalar T is greater than 0. The next set of conditions is T times minus infinity is infinity when the scalar T is less than 0. T times minus infinity is 0 when the scalar T is 0. And T times minus infinity is minus infinity when the scalar T is greater than 0. So this is this looks like scalar multiplication, multiplying a vector with a scalar. How do we do that? Using these conditions. And next, they have given t plus infinity equals infinity plus t equals infinity. This is the first condition. The second condition is t plus minus infinity equals minus infinity plus t equals minus infinity. The third condition says infinity plus infinity is infinity. And the fourth condition says minus infinity plus minus infinity is minus infinity. And the fifth condition says infinity plus minus infinity is 0. So what they are asking is, R union infinity union minus infinity a vector space over R? Explain. So what we have to do here is to check all the axioms on this space R union infinity union minus infinity. So first let us give a name to this. So I'll call it as M. M is nothing but R union infinity union minus infinity. So I have to check all these axioms. I know already that any scalar, say t, will satisfy commutativity, associativity, it will have an additive identity. So I don't really have problem with the scalars. The problem may or may not arise only when I take a combination of a scalar and a vector. So here these 5 axioms on top will help to see if there are any problems. So here t plus infinity equals infinity plus t. So commutativity is satisfied, and t plus minus infinity is minus infinity plus t equals minus infinity. Again commutativity is satisfied. So this condition is satisfied. Now to check associativity, what I can do is I can take, suppose, example, minus infinity plus infinity plus infinity. I can check this, and then I can check minus infinity plus infinity plus infinity. And if I get these two correct, then maybe it is associative as well. So minus infinity plus infinity is defined as 0. So 0 plus infinity is nothing but infinity. Now minus infinity plus infinity is nothing but infinity. And this is 0. So it is not associative. So this statement fails, and hence it can't be a vector space.